Thank you, Jan. It's really wonderful to be here. Thanks to Jan and Laurie for inviting me to the summer school, and what an amazing place to have it. So I got my hair cut yesterday, and the hairdresser was chatting to me, and they asked me what I was up to, and I said I was going to Italy to teach at a summer school on programming language implementation. And I don't think he knew what a programming language was, let alone what a programming language implementation was. But I tried to convince him of how excited I was to be here for a whole week of programming language implementation. I'm sorry I couldn't come for the whole week, but I hope you've been having a good time. OK, so a question for you. Who has used a compiler today? Hands up if you used a compiler today. Almost all. Today, yeah. Shouldn't have been, should you? Because you should have been watching the talks, not using a compiler. OK, who's used the compiler this week? All of you. Maybe I should ask, who hasn't used a compiler this week? Do we have any pure theoreticians in the room? OK, so then I might ask you, I guess theoreticians use the compiler in their mind, don't they? So you have, OK. So has anyone fallen foul of a compiler bug this week? Had a situation where a compiler has not done the right thing, in some sense of not doing the right thing? 2 or 3 times today. OK, so when I say compiler bug, what do you actually think of? What comes to mind when I say compiler bug? What ideas do you have about what might constitute a bug in a compiler? Say again? Semantics non-preservation. Very good. So the programming language has got a standard. The standard says certain things informally or formally about the semantics, and the compiler generates machine code that does not obey those rules. So that is, I would say, the worst kind of compiler bug, a wrong code compiler bug. I'm going to call that a miscompilation during these talks. What else might be a compiler bug? Yep. So someone nefarious has made a compiler, and the compiler deliberately doesn't do the right thing. You compile a compiler with that compiler, and then your compiler's got a bug in it, and someone can maybe exploit that bug if they knew about the intruder. Yep. OK. So I agree that that is a potential risk, and there's been some interesting blog posts about that kind of thing recently. But so yeah, but I guess that would still come down to a wrong code compiler bug. So what other compiler bugs might there be? Yep. So that's so the idea is that you make some small change in your program, and an optimization still fires when it should no longer fire. I would still class that as a wrong code compiler bug. That's probably, I think you've done a good job of hypothesizing the cause of a wrong code compiler bug. An optimization has got some preconditions. Those preconditions are not strong enough, and therefore the optimization does things that it shouldn't do. OK? So what other kinds of bugs might of a different nature? Yeah. Absolutely. So a performance bug then. So yeah, you want the compiler to generate good code for you. So arguably there's a performance bug in the compiler if it generates code that is very slow when there's no reason for it to be very slow. So that's another category bug that I'm not going to say anything about today. Okay. What else though? Yep. The compiler loops forever. Very good. I'll show you one of those later, right? The compiler doesn't terminate, doesn't finish compiling. Related to that, the compiler might, what else related to termination? It might generate a non-terminating machine code program for a terminating source program. That would be another kind of bug. Yep. Very good. So if you don't have a specification, what does it even mean for the compiler to have a bug? I prefer programming language with no specifications, because then your compiler can't be wrong. That's a good point, which I will come to shortly. So there's also the case that a compiler can crash, right? A compiler can crash like any other program. That could be a real problem if it's a JIT compiler and it doesn't crash, but it's got some, say, buffer overflow that could be exploitable. Or if it's a compiler for the OpenGL shading language, GLSL, which is a favorite language of mine, then that compiler runs at runtime. You've got an application, maybe in a web browser, that compiles a shader at runtime. If that compiler crashes, you can't use the program that was going to use that shader. It's not like you can work around the compiler bug. Like, I work around compiler bugs when I do offline compilation. If you're doing online compilation, you can't work around a compiler bug for a compiler that you didn't even know existed when you wrote the program. There can also be cases where the compiler doesn't reject a program it should reject. You give it some program that is not actually a program in the language, and it accepts the program anyway, and maybe generates some machine code, which could be bad because then you perhaps think that's a real program, and you try and deploy it and compile it with another compiler, and it doesn't work. And another category that springs to mind is that you give the compiler a malformed program, and the compiler crashes instead of gracefully rejecting the malformed program. OK, those are all the things I can think of right now. I don't know if you've got any more ideas. Let me know if you do. So why should we test programming language implementations? And by the way, I'm going to use the word compiler and programming language implementation pretty much interchangeably. I'll mainly say compiler, but almost everything I'm saying now equally applies to interpreters, JIT compilers, as well as standard offline compilers. So clearly, we'd ultimately like to avoid bugs that might affect the quality, reliability, and security of software for end users. So it would be a real pain if an end user has a malfunctioning application due to a compiler bug. Now, that's perhaps not all that likely to happen, although it does happen in practice, but it's not that likely. Why? Who gets the hard time? Not the end user, but the developer, right? So the developer wastes a lot of time trying to debug their code, and in the end comes to the conclusion that there's a bug in the compiler. And the really frustrating thing about a bug in a compiler is you can't necessarily get a fix for it quickly. You have to come up with some elaborate workaround for the compiler bug. This is something that I experience in my research quite a lot. I do a lot of research on the OpenGL programming model that you use for programming GPUs. And OpenGL compilers are not that mature, and we're trying to do some things that really push them to the limits of what they can do. And we frequently have compiler bugs that we have to work around, and it is really quite painful. You don't get this so much with C compilers or Java compilers because the languages are so much more widely used. Okay, so we'd like to equip developers with better tools by making their compilers reliable. And if you're interested in static analysis, which I am as well, then you would like to know that if you do some source-level analysis, that your program is going to be correctly compiled into machine code or into another programming language in a manner that preserves the semantics of the source program because you analyze the source program. So if you do binary-level analysis, this isn't a problem, but if you do source-level analysis, then you're implicitly placing trust in the underlying compiler, and you'd like it to be reliable. Okay. Another thing I would say, and this is something I would say to any of you who are thinking about doing a PhD, and this is something my PhD supervisor said to me for our first project. We were studying these weird graphs and their symmetries, and she said to me, Alastair, you've got to remember, these symmetries are interesting as objects of study in their own right. And as a researcher, I really like that. I take comfort from that. I often think there are things that just get me excited, and I think I can get other people excited about, and they're just fundamentally interesting. So I think compilers are really complicated pieces of software that are quite closed in the sense that you give them a program, they produce an executable, so they're quite nice to test, but they're hard to test. And I think they make fascinating objects of study in their own right. And in whatever domain you're working in, I wouldn't forget that. Things could be interesting just for the sake of it. They don't have to always have impact. They don't always have to solve other people's problems. And I think that's good because much research you do won't solve other people's problems. That's a guarantee. Although I'm sure lots of it will. Okay, so how do you think or know how programming language implementations are tested in practice? Before that, I have a question about yeah. 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 Yes, I would call that a compiler bug, and that's not something I'm going to cover in these lectures, but it's something I actively would like to start working on because it's very difficult to detect with certainty when such a bug has happened because naturally different programs have different runtimes, and it's not like there's a discrete change from an acceptable runtime to an unacceptable runtime. But indeed, the notion of performance bug is something that compiler writers take seriously. And in my work on graphics testing, actually, the companies often say, yes, yes, all these correctness bugs are all very well, but what about performance bugs? Because in some sense, these graphics people care more about performance than they do about correctness, which bothers me as a formal verification person. Okay, so what ideas do you have about how compilers are tested in practice at the moment? What do you think folks do in industry? Fuzzing, okay? So, yes, but what do you think they do before fuzzing? Unit testing. Actually, not so much, right? So can you say what you mean by unit testing in this context? Yeah, checking, yeah. So unit testing is a fantastic thing to do. The difficulty of unit testing a compiler is sometimes it's incredibly laborious to construct a control flow graph by using new block, make an edge from this block to that block, make a statement, make an expression, to make a control flow graph, and then run a data flow analysis on the control flow graph, and then assert some property of the data flow analysis. So actually, my experience is that compilers are not that well unit tested. Rather, people tend to write little programs and integration test the compiler, but they write a program that's going to have the control flow graph they want, and they know that a certain data flow analysis will probably get run, and then they can check the result. Yeah? So yeah, function level unit testing is not that common because it's actually very cumbersome. Okay, so what other ideas? Yep. Stat solvers. I would say stat solvers are not that widely used to test compilers in industry, but there was really interesting work from PLDI last year about this alive project on testing peephole optimizations using stat solvers. And I think a triumph of that work was it showed you could use stat solvers to find bugs in LLVM. And those bugs have been fixed and committed. I don't know whether that's being widely adopted, but it's really exciting. They use it in ARM. OK, cool. That's very cool to hear. Right. So before you think of fuzzing stat solving, what would you do? Yeah? Yep. Very good. So I used to work at a compiler company called Codeplay in Edinburgh, and they were writing a C++ compiler from scratch, and being able to compile Boost was this thing that they were aiming for. There was lots of C++ that the compiler could compile very well, but it couldn't compile all of Boost, so trying to compile Boost was a massive challenge for a compiler. OK, so more generally, regression test suites. Every compiler company or open source project has a large collection of programs that have been gathered over many years, mainly in response to bugs in the compiler. And these are little programs that have been constructed to minimally reproduce the bug. The bug has been fixed, but that test is run every time. So this is like standard regression testing in any kind of software application, but in the context of compilers. Another thing is conformance test suites. So some programming languages, especially new programming languages that are going to be supported by multiple platform vendors, often come with a conformance test suite. So in my world of graphics, which I'm quite invested in at the moment, there is an OpenGL conformance test suite, an OpenCL conformance test suite. And if you would like to get approval from the organization who make those language standards, you've got to pass their conformance tests. So these tests basically go through features of the programming language in isolation and check that the compiler does the right thing on each feature of the programming language. So can anyone speculate why conformance tests are not that useful? And the key word here is isolation. Yeah. Exactly. And interactions is where everything goes wrong. So conformance tests check things in isolation, and regression tests tend to check interactions that people didn't anticipate, for which someone then found a bug. The bug got minimized, and we end up with a nice test case exposing some optimizer bug that happens due to a combination of templates and structs and inlining, say. OK. Of course, a massive source of testing which leads to regression test suites is end users using the language. So if a language is sufficiently widely used and a compiler has been sufficiently rigorously developed, you're not going to find low-hanging fruit if you search for bugs in that compiler. You're going to find obscure bugs about unions inside unions, or a struct with 10 arrays inside it, and one of the arrays is an array of structs with a union inside it. You're not going to find a bug related to the assignment operator, I would hope, because of users using the programming language. If you're making a new programming language, you probably will. And then, as someone already mentioned, fuzzing, which is, in general, a term for random input generation, and therefore in the compiler world, a term for random program generation. Fuzzing has been shown by various researchers worldwide and for decades, but I would say especially by the efforts of John Regere's group at the University of Utah, to be very useful for finding bugs in compilers. And I'm going to talk a lot about fuzzing during these lectures. OK, I should say a quick word about formal verification. So it would be great if we could actually prove that a compiler is correct. Have a specification for the programming language at source, a specification for the target language, and actually formally prove that the compiler preserves the semantics of the source language when generating code for the target language. And the CompCert project is evidence that this can be done for a very large subset of C and can be done successfully. That's the real triumph. However, this was a massive undertaking that's still ongoing, and the truth is that most programming languages have compilers that are not actually verification ready. They're not clean room compilers that have been designed from scratch. They're big, ugly compilers that do lots of optimizations, target lots of platforms, and they're not correct, and they probably won't ever be correct. Therefore, we won't be able to prove they're correct. We can still use them in our day-to-day life, despite them not being correct, and we'd like to test them as much as we can to try to make them more and more correct. So I think at the moment, although I would very much encourage more research in formal verification of compilers, and I think one day this could be something that is absolutely mainstream, I think it's a long way off being so. But it's really important, say, in the aviation industry, where you would like to use an embedded subset of C, you don't care that much about performance, you want real-time guarantees, you want correctness, otherwise people die, so then you do really want to use some kind of verified compiler if you can. OK, so the focus of these lectures is going to be on testing. So now, why are programming language implementations difficult to test? So some of these points have come up already, but let me go through them. So the main factor which relates to the other factors is the absence of an oracle. So in testing, an oracle is some means for knowing the expected output for a given input when you run a program on that input. And most research in testing assumes the existence of an oracle for the system under test. The problem with programming languages is that in general, as I will argue in the next slides, we don't tend to have an oracle for a programming language implementation. And this is related to various other issues. For example, the problem of languages having undefined implementation defined and unspecified behaviors. The problem of non-determinism in a programming language that can make it very difficult to know what a program should do. And as someone at the back mentioned, the problem that some languages are either deliberately or not deliberately not that well specified. Their semantics are either deliberately unspecified or the specification is simply ambiguous and it's not possible to quite say what the right result or what an acceptable result for a program is when the program executes. So let's go through some of these in a bit of detail. First of all, have a look at this piece of code. This is a piece of code in the OpenGL shading language. And I really just mean have a look at it. I mean, don't try and read it in detail, but just look and see that it's not machine generated. It's not that complicated, but it is complicated enough that I presume none of you can see what the program's supposed to do. Okay? So now, should it produce this image? Well, how could we check? How long would it take? We could run the program and see if it does produce that image, but that doesn't tell us if it should, does it? So we run this program with our favorite OpenGL compiler, and it gives us that image. Well, that might just be that I used that compiler to generate the slide, right? That doesn't mean that it's the correct image. So how could we check? We could work out every image pixel color individually, and we could read the program for a year, and we could do hand calculations, and we could read the spec and see what exactly the rounding rules for sine and cosine are, and then we could eventually come to the conclusion that it does give the right image or that it doesn't. But that's not going to be feasible to do in practice. How long would it take to find out for sure? Perhaps a very long time. Does the question even have a clear-cut answer? Does even in theory there exists an oracle to say whether the program I sketched on the previous slide should render this image when you run it on your GPU? Well, actually, no, there doesn't. Because the OpenGL shading language specification says about floating point, any denormalized value, that's a very small floating point number, can be flushed to 0. Not must be, can be. The rounding mode cannot be set and is undefined. That means that it's got to be one of the IEEE rounding modes if you're into floating point, but you can't know which one, and you can't say which one you want. And nans, that's not a number values that you get if you do some crazy things with floating point, they are not required to be generated. That is, they might or might not be generated. Okay, so now you might think, well, Matt showed us how to do abstract interpretation. We could build an abstract interpreter that captures all these constraints. It over-approximates all the possible rounding modes, all the possible whether nans are generated or not. It captures all the possible cases of whether denormalized values are going to be flushed. But then the spec goes on to say this. Without any precision qualifiers, implementations are permitted to perform such optimizations that effectively modify the order or number of operations used to evaluate an expression, even if those optimizations may produce slightly different results relative to unoptimized code. So if you do graphics programming, this is really good news, because what you want to do is make things look like explosions. You just want it to look like an explosion, and you want it to look like an explosion as quickly as possible, and you don't mind if that orange is this RGB value or that RGB value, as long as it's roughly that orange. If you're trying to test the compiler, then this is a real problem, because there's no actual notion of exactly what the correct output for this program should be. So even in theory, there does not exist an oracle for this programming language. So there's no oracle. But people use this programming language. There clearly is a notion of unacceptable compilation. It wouldn't be OK just to say that every floating point operation returns 0. That might meet this text, right? Depending on your notion of slightly different. But clearly that would be unacceptable. So this is a programming language that is widely used, for which there is a notion of the compiler totally messing up, like reading from undefined values. But there's also the notion of the compiler doing transformations that lead to unpredictable, hopefully small changes in the program under analysis. So can you see why this is quite a hard problem, how to test this kind of compiler? Yeah. OK. Even if the language is precise, so let's say we've got a programming language that's completely formally specified. In principle, we could have a golden reference to that programming language, and we could use that as an oracle. So you could sit down and you could write the most perfect implementation of this language ever, and then you could compare other implementations against that implementation. But this seems a bit like a catch-22 situation. I mean, how are you going to actually implement that language? OK, you can read the spec and try and follow it really carefully. You may actually be able to formalize the language and use a mechanical theorem prover to prove that the implementation is totally rigorous. Some of my colleagues at Imperial College London have been doing that for JavaScript, for example. But in general, writing the golden reference for, say, C++ is going to be really challenging, essentially as challenging as building a full-blown C++ compiler. Maybe not quite as challenging because you wouldn't have to optimize the golden reference, but it's hard. So there's the question of whether you can then trust the golden reference. And for a large language, people probably prefer to invest their time into building real implementations of the language rather than reference implementations of the language. Okay, so a little bit of history for you. In 1982, when I was 1, Elaine Veilcher wrote a very cool paper called On Testing Non-Testable Programs. And this sounds like a contradictory title, but she makes what I think is quite a useful definition in this paper. If either of the following two conditions occur, a program should be considered non-testable. And the two conditions are, number one, there does not exist an oracle. Sorry, let's just say an oracle. And number two, it is theoretically possible, but practically too difficult to determine the correct output. So in the case of the OpenGL shading language, I think I demonstrated to you that there doesn't exist an oracle. The spec is sufficiently vague that there just isn't an oracle. In the case of a language like C++, in theory, you've got this 1,000-page document, and you could read that document and build a reference implementation, but practically that's too hard to do with absolute confidence. So I think there's an argument for saying that compilers for mainstream languages are non-testable in the sense defined here. By the way, why do you think that the OpenGL shading language has got those really, really vague rules about floating point? Yeah. The fuse, multiply, add. Okay, so that's a good answer. So fuse, multiply, add is a special instruction that many processors have where you can do a multiply and an add operation in one instruction, and you don't do intermediate rounding. So you don't multiply, round, add, round. You multiply and add and then round, and you can get better precision that way. So that is a reason why you might get variations. Yeah. But you might expect those variations to be predictable or bounded. Okay? But going further, it's not just because of fuse, multiply, add. More generally, it's because there were these different companies with different GPUs using different programming languages. And they wanted an umbrella programming language that they could all use, and everyone agreed that that was a good thing to do. But no vendor would be happy if that language's semantics gave an advantage to one of their competitors. If the language's semantics tried to exactly formalize, say, what NVIDIA GPUs do with floating point, then AMD, or ATI as they used to be, would have not been happy. So instead, the designers of that language came up with a deliberately vague umbrella semantics that allows all the vendors to do what they like, hopefully doing something reasonable. The whole point is they should do something reasonable within this umbrella. And that way, there can be somewhat portable graphics, rather than having portable graphics that's slow for some vendors, or having fragmented different programming languages for graphics. OK. So if we want to look for compiler crashes, cases where the compiler crashes during compilation, then the oracle is easy here. All we need to do is run the compiler on a valid program. So we need to have some idea whether the program is valid. And then we need to check whether the compiler's return code is 0, and maybe grep for some string in the output, perhaps fatal error. I mean, it might be enough just that the compiler doesn't give return code 0, but we might be looking for, say, fatal compiler errors. But what about an oracle for correctness of generated code? This is the really hard one. So what would you do? You would take a valid program and run the compiler on it. You'd run the generated executable. You'd capture its output. And then what? The question is, the compiler produced a binary. I ran the binary, and it did something. How do I know that that something is the right thing, or, in the case of a language that's got umbrella semantics, a right thing? Because there may be multiple right things you could do. Yep. Absolutely. If you had a program where you knew what the output should be, then you could use that program to test a compiler. So programs with known expected outputs, i.e. programs that already have oracles, that certainly would help. Yep. OK. But in general, you can see for arbitrary programs, this is challenging. So how can we tell whether the captured output is acceptable? That's what the problem boils down to. OK, so before we go any further, let me give you an intermission. I've talked a lot about compiler bugs, but why don't I show you a compiler bug? So what I did in preparing these slides was I decided I would use that laptop, which had Visual Studio 2015 installed on it. So I Googled for, I got the compiler version, and I Googled for compiler crash bug for this compiler version, and a page came up, and I could reproduce the compiler bug. So this is a compiler bug that I found on the internet recently. And I just want to illustrate that these bugs really happen. They really hinder people. This is a bug that someone didn't find with a fuzzer. This is a bug that someone found because they were trying to write some software, and it crashed the compiler. I want to just emphasize, I'm only using Microsoft's compiler here because it's easy to demo. Compiler crash bugs are fairly common, and there are plenty of them in GCC and LLVM, too. So no offense to Microsoft here. Right. Let me leave the presentation for a moment and go into Visual Studio. So what you'll see here, is this readable enough at the back? Yep. So what you'll see here is a little program that someone posted online and have a look. It's a program that does some vector manipulation. It's not a full-blown program. It's a relatively small test case. But you can see it's not some contrived example that uses really crazy language features. It's a pretty small program. So if I go to my command prompt and I run Microsoft's compiler, so CL, the command line compiler, we're on this program. So it's called VS 2015 crash. Then the program compiles and we get a binary. Now, if I run this with O2, which is some optimizations, then what we get here is internal compiler error in cl.exe, which is the command line compiler. And what it says here is that the problem was triggered by line 26 of the source file. A fatal error occurred. It doesn't give us details of the fatal error, because typically when in a compiler you call the fatal error function, you don't tend to explain why the fatal error happened. You tend to just say there was a fatal error. Please tell us. And then what I quite like is it says somewhere, yeah, try simplifying or changing the program near the locations listed. So this is what you tend to do when you have a compiler crash, right? You tend to simplify or change the program near the locations listed. So let's try that. So I think it was line 26 that the program occurred. This one, yeah? So we've got a type called test struct, and we've made a test struct called test, and we've given it the static initializer 0. So what I'm going to do here is, instead of doing that, I'm going to just not initialize the struct, and I'm going to say test.size.x becomes equal to 0, and test.size.y becomes equal to 0. If I remember rightly, initializing it to 0 will 0 all of the fields if we don't specify those fields. So this should have the same effect. And now if I compile this program with optimizations, then it compiles fine. So this is an instance of a simple program that gives a compiler fatal error and a simple workaround to that fatal error. Okay, just undo this so I don't get a git change when I look at this later. Any questions about that example? Other than why did it happen? Like, I can't answer that. Okay, so by the way, I also tried this on Visual Studio 2017 and the bug is gone. So let's talk a little bit about undefined and unspecified behavior, in case you haven't studied this much. So this is something that's particularly a problem in languages derived from C, but it does affect other languages too. Less so Java, and I don't know whether Haskell has got any undefined behavior. Is anyone in Haskell? Is there such thing as an undefined behavior in Haskell? Yeah. Haskell doesn't have a formal spec? What? I thought GHC was the formal spec. I thought GHC was the formal spec. It's written in Haskell, right? No, I know, yeah, I know. I was joking. Yeah, yeah, no, so Haskell doesn't have a formal spec, okay. Yeah. But what I mean is it's not, okay, I'll show you what undefined behavior means in C, and then you can tell me whether Haskell has an equivalent. Suresh, you can. And it has undefined behavior? No undefined behavior, okay, cool.
So Haskell almost certainly has to, because it uses LLVM.
Right.
As an option.
Okay. Is that an implementation detail?
Yes, right, but it's an implementation detail that matters for the behavior, because they're building on something that has tons of undefined behavior.
Right. Okay. And yeah, and I believe there's this unsafe perform IO. Someone told me that Haskell's really great. Oh, let's not go any further. Right. Okay, so in principle, can we predict the output of a program P if the language is quite formally specified? Well, not always. If P exhibits these two things, undefined or unspecified behavior, then the situation is pretty complicated. I'm going to focus here on the case of C-like languages. So in C, the behavior of a program is completely undefined for an input that triggers an undefined behavior. So if the program can do something like a division by 0 on a given input, it's not just the case that that division by 0 might crash the program or might lead to a funny result. It's the case that you've really got no guarantee that anything you expected will happen on that particular input. And I'll show you this in action a bit later on. Unspecified behavior is not quite as bad. It's behavior that can change between compilers and optimization levels. So I'll give a couple of examples. But the essential thing is that these problems make the oracle problem even worse. It's not just that you've got a nice language with proper semantics that are complicated, for which it's hard to know what the results should be. You've also got these undefined behaviors that make it very difficult to work out when you can even expect a result. So C has got loads of undefined behaviors, but the classic ones that people know about are division by zero and accessing invalid memory. Something a little bit less well known is that signed arithmetic, when it overflows, is an undefined behavior. That's something I didn't know until a few years ago. I assumed that the semantics was 2's complement arithmetic, and when you did overflow, you got wraparound behavior. And indeed, plenty of code depends upon that happening, and it often does happen. But actually, it's not what the spec mandates. It's an undefined behavior. And I'll show you later how, even with a compiler for an x86 platform where the machine does have that semantics, strange things can happen if you assume your program has got wraparound behavior for signed arithmetic. OK, so a program that exhibits one of these has no meaning for an input that triggers the undefined behavior. The program might have lots of syntactic cases where you could get undefined behavior, and it has meaning unless you've got an input that hits one of those syntactic points and causes the undefined behavior. Yeah. That's right, yeah, the taming undefined behavior in LLVM coming out this year's PLDI. Yep. He sent it to me, and I have yet to read it, but it looks really, it looks really interesting. OK, so unspecified behavior, a classic one in C is that the order of function argument evaluation is not specified. So if you write something like, you call a function foo, let's say it takes 3 integers, and let's say you've got some functions f, g, and h at your disposal that all return integers. If you call foo with the arguments supplied by the result of f, the result of g, and the result of h, then you've got no guarantee on the order in which f, g, and h will get called. And if they're side effect free, that doesn't matter. But if they have side effects, and if those side effects interact with one another, then this order can actually influence the outcome of your program. So you're allowed to write this in C. You just shouldn't depend upon the order. And it's not as if that compiler has this order, that compiler has that order, that compiler has that order. The point is, compiler optimizations could, in principle, change the order. So it could be that changing the optimization settings or upgrading to a newer version of the same compiler could change what your program does. So there will be some order invocation, but you can't depend on which order. OK, and then implementation-defined behavior is much less of a problem. This just basically says that a compiler has got certain flexibility for some operations. It must commit to an implementation and always use that implementation. But the spec gives an envelope of possible behavior here. And classic examples in C include the widths of various primitive data types. So if you're using a certain compiler, it will use a certain integer width and a certain pointer width. And you may be able to control that on the command line. It won't change under your feet. But if you want to compare that compiler with that compiler, then you've got to take care to see whether they use the same assumptions about integer widths. And if they don't, you should make sure you're only comparing them on programs that don't depend on those widths. Another example is endianness, so the internal bit patterns inside integer data, and things like the rounding of transcendental functions, such as the sign function, when you're dealing with floating point. OK, so if we want to compare results between compilers, then we should be aware of implementation-defined behavior before we start to say that one compiler is buggy because it deviates from what another compiler does. Then the next problem is non-determinism. So we're going to look at a few different compiler testing techniques that circumvent this oracle problem via some kind of cross-checking. And if you've got a program that's got non-deterministic behavior, where between runs the program can genuinely give different results, that makes it really difficult to cross-check 2 different compilers with that program, because it's hard to tell the difference between a compiler bug leading to a difference or acceptable non-determinism leading to a difference. All right. And then the final thing is this lack of programming language semantics, which we already covered. But just to reiterate, this quote from the GL spec, if those optimizations produce slightly different results, that's OK. This makes it very difficult to do this kind of testing. OK, and as I mentioned already, despite these problems, these compilers exist, and they need to be tested. They need to be analyzed. So the summary so far, then, is I hope I've convinced you that we would like to test compilers. We'd like to make them more reliable. And I hope I've also convinced you that, in general, we don't have an oracle to help us with our testing. So then the question is, what can we do about the oracle? And I'll now move on to that. But first of all, are there any questions about undefined behavior, implementation-defined behavior, lack of a semantics, anything like that before we move on? OK, please do feel free to shout out if you do have questions during. I would be keen to answer them. Right, so what can we do? One thing we can do is undertake testing in limited scenarios where we do have an oracle, as this gentleman alluded to. Right, there may be test cases where we know what the answer should be. And another thing we can do is appeal to what are called pseudo-oracles, some means for obtaining indirect evidence of whether the compiler did the right thing or not. So we'll look a bit at the first point, and then we'll mainly look at pseudo-oracles. And the reason I labored the point about undefined behavior is that we've got to be very careful, whichever technique we use, we've got to be very careful about undefined behavior, because for languages like C that have these undefined behaviors, we can quickly think we found serious bugs when really there's no bug. Okay, so programs with known expected results. If we write some programs by hand, we can equip those programs with assertions at certain program points that check properties we know to be true of the programs. So for example, we might write a correct sorting routine, make sure that we actually write it down correctly. We might then write a test harness that runs the sorting routine on various inputs and checks that the outputs are as expected, or checks some properties of the outputs. Then we could compile and execute our test harness and run it, and if the tests fail, then we know, because the program was correct and we carefully crafted the inputs, we know that the compiler must be the weak link here. So this is certainly something one can do. And conformance tests for programming languages are written this way. You have little scenarios, you run them, and you've got expected results. And if the compiler doesn't agree, then there's something wrong with the compiler. Or with the tests, but if the tests are relatively simple, it's usually the compiler. Okay, regression tests are similar. They're written to close the door on known bugs. Another thing we could do is try and generate these programs automatically in a manner such that their results are known. There's not so much work on that, but some people have tried this, having a program generator that can generate many, many programs in a clever way so that by construction, the program is guaranteed to produce this result, or the result it produces is guaranteed to have a certain property, and we can automatically test those programs. A related idea, which I don't know if people have explored as much as perhaps they should, is partial oracle inference. So suppose you've got some existing code from the wild. You might run some static analysis on the code, infer some invariants about the code, and then you could plug in assertions of those invariants into the program, and then you could use those assertions as tests of your compiler. So, for example, we might have a little bit of code like this. Okay, we've got some if statement with a non-trivial condition. And if this condition holds, then we continue. We're inside a loop here. So certainly we know, after the if condition, various facts, and in particular, we know that x cannot be 0. Because if x was 0, it would be less than 1. And because these are disjunctions, we would definitely hit the continue. So this is a fact, one of many facts I could have picked, that should be true at that program point. And if the compiler fails that assertion when you run the program, the compiler must have miscompiled the program. Yeah? If the compiler what, sir? Yeah, so the compiler might remove the assertion as a miscompilation. It might think the assertion is not reachable and remove it, and then you won't detect the bug. So all testing is prone to these kinds of incompletenesses. And indeed, a very weird thing when you're thinking about buggy artifacts is assumptions you make about how the artifact should behave may be contradicted by bugs in the artifact. Yeah. So this might catch the kind of bug where the compiler has miscompiled this condition, but not removed the assertion, and then you'll find that bug. If the compiler has miscompiled the condition and removed the assertion, or meant the control flow jumps down to there or something, then sure, you won't find the bug on this test case. And hopefully you'd find it with some other test case. Of course, with any kind of testing, there will be bugs you just won't find. Okay? So if the assertion fails, then the program has been miscompiled. So let's now look at a wrong code bug in Microsoft Visual Studio. And actually, you'll see that I got this example from this wrong code compiler bug. And once again, I'm just using Microsoft compiler as an example here. So let's go back to Visual Studio. And I've got this file called wrongcode.cpp. And again, this is something I found on the internet just by searching for Visual Studio wrong code bug. I put the compiler version in, and someone came up saying, I'm having this problem, blah, 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 blah. And this is their code. So what they have is exactly that condition I showed you. So, excuse me. If this condition holds, continue, and then assert x not equals 0. So I don't think the assertion, say again, sorry. Thanks. Sorry, okay. This is the condition I showed you in the previous slide. This is the assertion. Okay, so if I compile this, which is called VS 2015 wrong code. Then I run it. Then the program doesn't terminate incorrectly, and it doesn't produce any output because it wasn't supposed to. Now, if I enable optimizations, then we should find that the assertion fails at line 29. Right? So this is an example where the compiler is messed up and the assertion fails. Okay. So we call this a wrong code compiler bug because the bug is totally silent. Let me explain why the bug is totally silent. We had an assertion in the program, and the program failed that assertion when executing, but the compiler gave us no indication that something went wrong when it compiled the program. If we didn't have that assertion in the program would just execute and do the wrong thing. Okay? So the assertion was only there because the person reporting the bug wanted to illustrate the bug. Presumably they found the bug by actually running the program on some real data and producing some results, probably in a larger context. But there are clear limitations to this business of relying on programs with expected known results. Writing tests by hand doesn't scale. And also, humans are not that creative in terms of thinking about really weird scenarios to test. So we might not reveal very subtle defects by writing programs by hand. And generating programs scales, but frankly, all the ideas that I have about generating programs where the results are expected, the programs that I would generate would be fairly idiomatic. They would use kind of tricks to know what the result would be, and I don't think they would test real corner cases of the compiler. So I think that the richness of generated programs would be limited by this requirement to have known results. And another problem is, if you want to actually debug a wrong code compiler bug, you need a small example. Like that example I showed you there was pretty small. You don't want to, say, have a 2,000-line program or a 5,000-line program and that gives a different result with a different compiler or doesn't, this assertion fails in a massive program. That's no good to a compiler developer trying to work out what's wrong with a compiler. They need small examples. So automatically generating small examples with expected known outputs that are good at triggering compiler bugs, that seems like a hard problem. And large programs are hard to debug. And this business of augmented programs with assertions, I actually think that's a promising direction. To my knowledge, it's somewhat understudied. There's lots of work on invariant generation, but I don't know if people have used invariant generation for the purpose of testing PL implementations. If you know of work about that, then please let me know. But this also suffers a bit from the Heisenberg issue, which is where if you insert an assertion, that can inhibit a compiler bug. So the thing about compiler bugs is they usually arise due to optimizations gone wrong. And a compiler can't often optimize across an assertion. If the assertion is enabled, it's not disabled, the assertion can't be removed. You can't, for example, do some kind of code motion and move the assertion to another point in the program unless you can prove that the assertion would be reachable here if and only if it was reachable there. So it seems likely adding loads of assertions in a program is going to actually inhibit the kinds of optimizations a compiler is going to apply, and then you're probably not going to find bugs in those optimizations. Does that make sense? Yeah? So in general, this business of like, you try and measure the compiler by changing the program, and then you change what the compiler does with the program. Right. So the first pseudo-oracle we're going to look at is cross-checking between different implementations. So we don't have programs with known results. We don't have a golden reference, but we've got multiple compilers for a programming language. Then what we could do is actually cross-check results between those compilers. So we've got some test program. We compile the program with many compilers. We compare the results obtained by running the program, and let's imagine that these programs just print integers. Then if clang gives the integer 42 when we run its executable, as in we compile the program with clang, then we run the executable and we get the integer 42. And all the other compilers give the integer 24 when we run them, then this gives us a pretty strong piece of evidence that clang has miscompiled the program, despite having given the answer 42. But because the majority were different, it's likely clang got it wrong here. Okay, and this is known as differential testing. This is quite a widely used technique, not just in the domain of compilers, but in various areas of software engineering, where you have things that are hard to test, but you've got multiple implementations. You can cross-check them. You can do differential testing. So, question then, why is this only a pseudo-oracle? Why have I used the word pseudo here? Why is it not an oracle? Maybe all of them got it wrong, yeah, because maybe the answer is actually 15, right? And there's various compiler bugs, and all of the compilers are wrong. Yep. Absolutely. If we've got one compiler, we can do cross-checking using different options. Could be debug and release, could be 03, 02, 01, 0 in GCC, and we can treat them as if they were different compilers. And that's often easier than actually setting up multiple compilers, because sometimes, especially if you want to check maybe C programs that use GNU extensions, it's much easier to just test GCC with different optimization levels. Was there another question or comment? Yeah. Exactly. If the program's got undefined behavior, then they're all right because like I'd be right if I run the program in my head, I'm right because there's no meaning. Exactly. So, or if the program depends on implementation-defined behavior, and if Clang legitimately does something different from the other compilers, that could be the source. Yeah. So it's not. This sounds like really easy differential testing, but it's actually not so easy in practice because of these practical caveats. Okay. Any other thoughts at this stage? I think between you, you've eaten up 2 of the points on the next slide, which is very nice. Yeah.
At least something you get for running it all on different versions of the same compiler is that it's probably the case that the implementations used to be.
Absolutely. So using one compiler is really good. I think you've stolen another point from the next slide. Yep, very good. But keep going. Yes, if you stick with one compiler, the implementation-defined things will be the same, right? Unless the compiler manual actually says, if you enable this optimization, the integer width changes, which it's not going to do, then, yeah, indeed, you're safe from changes in implementation-defined behavior. Yeah. Okay, so the requirements for compiler cross-checking. The program needs to be deterministic. If the program isn't deterministic, then we can expect differences in results. It needs to be free from undefined and unspecified behavior, otherwise we can expect all kinds of results. Multiple compilers have got to exist. If this is your great new programming language and you're the developer of the first compiler from that language, then you're not going to be able to do differential testing on that programming language, right? Unless you convince a friend of yours to implement it. If it's the only implementation, then you just can't apply this approach. And the compilers have got to agree on implementation-defined behavior, or the program has got to not depend on implementation-defined behavior. One or other of those has got to hold. Otherwise, you may expect different results from different compilers. And as we already mentioned, we can cross-check multiple compiler optimization levels, like GCC 00 versus GCC 02, and this gets around the implementation differences issue, because it's one compiler with different settings. Yeah? Absolutely. A limitation of using the same implementation is there might just be some fundamental bug in the compiler that's not related to optimization, say, and then they're all going to trigger that bug, and then you won't see a difference in the results. Yep. So therefore, using multiple compilers can give you more diversity. Actually, something I think is kind of interesting, right? So I tried to, even though I like Windows, I find the Microsoft compiler not that friendly. Like the compiler options have got crazy names. So I tried to just find, and I also knew that John Regera has posted tons of bugs in GCC. So when I thought I would find some bugs to show you, I thought I'd look for GCC bugs. So I looked at Cygwin and thought, okay, which GCC version have I got in Cygwin? And I tried to find bugs in that GCC version. But I couldn't reproduce any of them. And presumably it's because, under Cygwin with different libraries, different header files, perhaps funny differences, those bugs weren't reproducible. And it really made me think that actually, and then with the Microsoft bug, because Windows is kind of Windows, it's the same, it works or it doesn't work. It's not like Linux where it depends on all these millions of components that you've got together. Kind of made me think, actually, there is real strength in diversity. If you've got, lots of people with diverse compilers compiling their applications, you're going to have many differently compiled applications with different bugs, but hopefully not this single point of failure where, the whole of Windows has been miscompiled, as we know from recent, well, I don't think it was miscompiled, but Windows has a bug, and then any Windows platform is potentially affected. So yeah, I was quite intrigued why I couldn't reproduce these GCC bugs under Cygwin. And what you said there about if you build on the same infrastructure, you're likely to suffer from the same bugs. This is a case where maybe by building on different infrastructure underneath, they weren't. Okay, so it's really frequent to use differential testing informally. If you think you found a compiler bug, often the first thing you do is try a different compiler. You're not thinking of, right, I'm going to do some differential testing. You're more thinking, okay, is it just me, or is this a problem? I'll try it with another compiler. That gives the result I expected. That adds to my evidence case that there's a problem with this compiler. So often you would say in a bug report, with GCC I find such and such, but with Clang I get something else. Or at 00 the result printed is this, at 02 the program segfolds. But you've got to be very careful before you report these bugs, because time and time again people report these bugs and the answer comes back, closed, won't fix. your program has undefined behavior, so there is no reason for GCC and Clang to behave consistently. Actually, this is much more polite than you'd probably get if you find these bugs. I think compiler developers are really pissed off with people just reporting undefined behavior problem after undefined behavior problem. Okay, so let's briefly test GCC and Microsoft's Visual Studio compiler differentially using that example I showed you. So I'll fly through this because it's pretty obvious, but what I can do here is I can say CL VS 2015. Oh, sorry. No. I wonder if there's a way of disabling that. Pretty much every talk I give has that problem. Right, wrong code, and I can do, if I remember rightly, very intuitively, FE VS no opt.exe. Yep. I think that's how I do it. Okay, so I've got an unoptimized version in VS no opt.exe, and let me have an optimized version in vs.exe. Excuse me, sorry. What I meant to do first, program, assertion, I added a print statement. So rather than asserting that x is not 0, I'm going to print x. The idea here being that, let's imagine the program didn't actually have that assertion in it. It used to print some output. So we might be more realistically testing a program that prints some stuff rather than a program with an assertion. So let me rerun those compile commands to compile this program and that program. And then let me go to Sigwin and let me do GCC -o GCC no opt. And I'm going to do VS 2015 wrong code printf.cpp. Okay, so opt. We get a load of numbers printed. Okay, so let me just put those numbers into a file, GCC no opt.txt. Let me run VS no opt. Put that into VS no opt.txt, and then let me run VS opt. So I've now got results from 3 different compilers. I've got Microsoft's compiler with no optimizations, Microsoft's compiler with optimizations, and GCC, which by default has no optimizations. And now let me look at the difference between VS no opt.txt and GCC no opt.txt. And my whip merge tool says the selected files are identical. So these compilers have led to programs that produce the same output, whereas if we compare VS no opt with VS opt.txt, then we get these programs these files that are different, right? They're different in the first character, and if I go down, I know the screen is staying the same, but it's like a repeating pattern. So I'm going down, and every so often there's a 0 where, well, I don't know what there should be instead because I didn't write this program. But anyway, the point is you can see that these compilers have led to very different output they've led to programs that generate very different output. All right. So that's one pseudo-oracle, which is cross-checking between compilers. So pseudo-oracle number 2, then, is cross-checking equivalent programs. Let's imagine that somehow we know that we've got a test program, test1.c. This could be in another language, by the way, but let's imagine C for now. That is equivalent in the sense that it should produce identical results to test2.c. And we know that that's equivalent to test3.c. Let's not worry for now about how we know this. Let's just imagine that we do. We can compile these all with one compiler. So GCC, for instance, but it can be any compiler. And we can compare the results. And if the results do not all agree, then there must be a bug in the compiler because the programs are all equivalent. So they should all give the same result. So rather than trying multiple compilers on one program, we're trying one compiler on multiple programs, but the programs are being chosen carefully so that they should give exactly the same results. Does that make sense? Okay, so what are the... Okay, so mismatches indicate bugs, and the majority is probably right, as before. So again, what are the problems with this technique? What are the things we need to be careful about? Undefined behavior, yeah, okay. So the program should be free from undefined behavior. What about implementation-defined behavior? Is that a problem here? It's not a problem. Why not? Same compiler, right? So we get around the implementation-defined behavior problem here. Do we need multiple implementations to exist? No. There can only be one implementation, and we can test it this way. So what's the real challenge here? Creating the equivalent programs in the beginning, having equivalent programs to use at the beginning. And this kind of testing is a form of metamorphic testing, which I'll tell you a little bit about tomorrow in more detail. So what are the requirements? Well, we need equivalent programs to do this. They could be fundamentally different implementations of the same algorithm, or maybe they might be vanilla and optimized versions of a routine. We might have, say, some image processing routine, and we might re-implement it using vector instructions, and we might want bit-level equivalence between those. If we've got those programs at our disposal, we could use those to do some compiler testing via equivalencing. We might derive programs from one another automatically via program transformations, such as refactorings, and I'm going to show you a little bit about my work on that topic tomorrow. And as discussed already, the programs have got to be deterministic, and they've got to be free from undefined and unspecified behavior, but they don't need to be free from implementation-defined behavior, because we're just using one implementation. And again, we frequently use this informally. If we write a bug report, then we often say things like, if I reverse the order of the then and else branches, the program compiles correctly. Or manually unrolling the loop makes the problem go away. Or if I extract these lines into a function, I don't see the issue. It's very common when you're trying to report a compiler bug to perhaps do a few things to the program that you don't think should change its meaning, but you observe do change what the program does when you run it. So just like we use differential testing informally when we're trying to understand bugs, we often use equivalencing informally for the same reason. And it's very common to be shot down from undefined behavior. And this time I can show you me being shot down due to undefined behavior rather than giving you a made-up slide. So look at this then. Roland Schneider changed bug 99919, so a lot of bugs, from new to resolved with invalid. This is not a bug. The shader has undefined output. I've confirmed the path taken through the shader in the opu function, and it's always the else clause, then not satisfying the if there, so the returned hit data value is always undefined due to using out instead of in out for the HD parameter. Okay, so this was something quite exciting that was then very disappointing. We've been doing this work on graphics compiler testing that I'll demo to you tomorrow, and we've got this series of blog posts where we basically show that we can find bugs in all of the compilers we tested, and which we found quite surprising, and it was quite exciting. And then we moved on to testing these open source compilers. We just tested proprietary compilers like NVIDIA drivers, AMD drivers, Intel drivers, Qualcomm, ARM, Imagination. I should name them all now. I've named almost all of them. I think Apple as well. Right. And then we moved on to testing these Mesa drivers. So Intel and AMD have got open source Linux drivers for their graphics cards based on this Mesa framework. And we set about testing them. And it's not as though I thought that I didn't have an expectation about open source being more or less reliable. I didn't really have a hypothesis. But because we found bugs in everything, I was totally sure we'd find bugs quite easily in them. And Mesa, we found this one and reported it, and they got shut down. And we tested and tested and tested and tested and tested, and just couldn't find a bug. But I think we have now, but haven't reported it yet. So apologies to the video if someone watches this and it was also shut down. Yep, so anyway, the point here is that I had two programs that looked equivalent. We found a mismatch in the Mesa compilers, but it turned out that actually the original program had undefined behavior. So our equivalent program also had undefined behavior, and then the compiler legitimately gave a different result because of the undefined behavior. Okay, so next intermission then. Let's look at doing equivalence testing of Microsoft Visual Studio Compiler. So what I've done is I've got VS no opt, VS 2015 wrong code, and I've got, oh sorry, same problem again. I've got it this time. VS 2015 wrong code equivalent. Okay? So what I've done here, I've made some changes to the comments, but basically, in the original program, there were two unsigned integers, x and y, which were declared as local variables. And in the equivalent program, what I've done is I've promoted those to be global variables. Right, so I've made them be global variables instead of local variables. So if I go up, you can see that on the right-hand side, we've got these global variable declarations. So under what conditions is that an equivalence-preserving transformation? What do I need to be careful of before I apply that transformation? Not a concurrent program? I would say yes, I agree with you, right? Because, yeah, it could be that, yeah, multiple threads could execute that function if you make these global. Yep, so it can't be a concurrent program. That wasn't what I was thinking of, but yes, I agree. What? Another condition? Recursion, very good. Okay, so let's say that function was recursive, then implicitly there are multiple copies of these local variables on the stack. If I promote them to global, now I've just got one copy of the variable, okay? But I checked, and this was not a recursive or concurrent program. And your automatic equivalence applier could also check that. What it wouldn't do is know where the bug was and apply a perfect transformation to expose the bug, which I did as a human, okay? But Anyway, I've applied this minimal change to the program that should preserve its semantics. And as I already showed you, if I do cl02 vs 2015 wrongcode.cpp and then run vs 2015 wrongcode.exe, then the assertion fails. If I instead compile wrongcode equivalent and run wrongcode equivalent, then the assertion doesn't fail. So promoting these locals to globals changed the compiler optimizations that were applied. Compilers tend to be much less aggressive in the presence of global variables because of inter-procedural analysis being expensive and also hard to get right when you've got multiple compilation units that you've got to compile together. So that change inhibited whatever optimization had gone wrong. Okay, so if we knew about the bug already, this wouldn't be worth doing. But let's say we didn't know, but we were looking for compiler bugs. We could apply these kinds of transformations randomly to many, many programs, and eventually this bug would have come out in the wash. So just to recap this section of the presentation then, to summarize some of the differences between cross-checking implementations via multiple compilers or cross-checking a single implementation across equivalence programs. Non-determinism is a problem for both approaches, as is undefined behavior and unspecified behavior. Implementation-defined behavior can't be tolerated when you cross-check multiple compilers. As we discussed, you can potentially get around this by using one compiler at different optimization levels, although then you won't find bugs that apply at all those optimization levels. If you use equivalent programs, then implementation-defined behaviors are not a problem. But of course, you can't do differential testing across compilers with only one compiler, whereas you can use equivalent programs with a single compiler. On the other hand, you can use a single program to differentially test multiple compilers. If you wanted to test one compiler with equivalent programs, you need to have those equivalent programs, and that may not be something that you have at your disposal. So both techniques are effective and have been quite widely used over the last few years to test the number of compilers in practice. And I'll elaborate in the remainder of the time today and tomorrow on some of the techniques behind that. Okay, so if you want to apply either technique at scale, you need a large set of programs. So if you want to apply equivalencing across programs, you need, for a given program, many equivalent programs, but you probably also need a bunch of families of equivalent programs. It's not the case you need one program and loads of variants of that program. You probably need loads of variants of this program, loads of variants of that program, loads of variants of that program. If you want to do differential testing, you need a very large set of interesting programs that are free from undefined behavior. And getting big sets of programs is quite challenging, so we can actually resort to program generation to get these automatically. And we'll come onto program generation in a while. Okay, I'm now going to talk in more detail about undefined behavior, because I think it's really interesting and ill understood. But before I do that, are there any questions or comments on what I've said so far? Okay, so undefined behavior in more detail. So as I've already said, compiler testing for C-based languages is very hard because of undefined behavior. And I think undefined behavior is one of these things that is just fascinating in its own right. It's like, humans have created this horrible thing, now let's try and understand its ramifications. And I think that the horrible thing is not that well understood. I certainly didn't understand it that well until a couple of years ago. So I'm going to go through some of the things that I thought were really interesting related to undefined behavior. Okay, so I'm going to motivate this by trying to implement saturated addition for signed integers in the C programming language. What do I mean by saturated addition? Well, I mean that if I take two integers and add them, I should get the mathematical sum of those integers, unless that number would not be representable. In which case, if it would be too large positively, I want the biggest possible positive integer. And if it would be too large negatively, I want the negative number with the biggest possible magnitude. Does that make sense? Yep. Okay, so this saturated addition can be quite a useful operation to have in practice. Right. So I'm going to do something criminal here. I'm going to edit code in Visual Studio and then compile it with GCC. Don't know if that's allowed, but I'm going to do it. Right, so I've got a skeleton here called addsat. Takes two integers, x and y, and returns an integer. And what I want is addsat to give me the saturated sum of x and y. So I'm going to have a go at writing this in a way that would work if we had wraparound semantics. I'm going to say, if x is larger than 0, and y is larger than 0, and x plus y is less than 0, then return int max. So I'm saying if I've got two positive numbers and I add them together, then I should get a positive result. If I get a negative result, that indicates that the integers have been added together and wrapped around to give a negative result. So I know the overflow occurred, so I want to return int max. Okay, if on the other hand, x is less than 0 and y is less than 0, and x plus y is positive, then I want to return int min, because the reverse has happened. I've got two negative numbers added together. I should get a very negative number, but I got a positive number, so I want to return int min. And otherwise, I want to return x plus y. So let me write a little harness for this. I can never remember whether argc or argv comes first, so that's why I pre-prepared this. So I'm going to say here, int a equals a to I, or à trois, as I like to call it, argv1, and int b equals à trois of argv2. What's the a for? ASCII? I suppose, yeah. Okay, so saturated add of integer and integer is integer, where the integers we care about a, b, and add sat of a, b. Okay. Happy? Yeah? Can I use you as human type checkers for a minute? Does it look okay in terms of typing? I think so. Right. So gcc -o main add sat dot c. Okay, so main 10, 20. Saturated out of 10, 20 is 30. Main 120. Saturated out of 120 is 120. So that's fine. It seems to be working okay on normally sized numbers. Let's try some big numbers. Okay, looks all right. And at some point, we should get the saturation. Just keep adding zeros. I think one more should do it. Bang, okay? So if we add these two very large integers, we get what you might recognize as the largest representable signed 32-bit integer, one of my favorite numbers. Okay, so that looks good. So now let's compile the program again, but let's compile it with optimizations. Okay, and let's just try a couple of these. Let's try 100, 100. Good. Let's try 1,000, 1,000. Good. Okay, now let's try the big one. So the saturated add of this very large number, and this very large number is this very negative number, right? So that seems pretty weird. So I went to GCC and I filed a bug report and I said, your compiler is buggy. Yeah, okay, I didn't really. But people have done. So why did we get this really strange result where when we compile with no optimizations, we get the desired saturating addition? When we compile with optimizations, we get this completely crazy result where we add these two large numbers and we get precisely what we try to avoid with our saturating addition function. It's almost like we had just used normal addition. Okay, so let's explain what's happening here. Right, this is the program we just wrote, and we just saw it in action. Right, which results are correct? Without optimizations, we got that the saturating out of these big numbers was this saturated number. With optimizations, we got something different. Clearly, the top result is what we wanted, but which is correct in terms of what the program says and what the compiler did? And the answer is both or neither, depending on your viewpoint, right? I would say the answer is both. Both are correct. The reason is that the behavior of a C program is undefined for inputs that cause signed arithmetic overflow. So if your program exhibits overflow, its behavior is undefined. It's not the case that if you detect it's done overflow, you should do something funny. Even if you detect it has exhibited overflow, then it has exhibited overflow, and therefore it's undefined, right? So you have to do something more clever. You have to work out that it would exhibit overflow if you would add these numbers. You can't actually add them. It's really frustrating. You've got to basically determine using some arithmetic whether their sum would be too large to represent. Or you can cast them to a larger type, add them, and then ask if they're now too big, right? So technically, it would be fine for the program to print gotcha or exhibit any other behavior. So technically speaking, the program's behavior is totally undefined on these inputs. So an exercise for, I took this from a a course I teach, an exercise for the students was to add this without, to write this function without invoking undefined behavior. I'm not going to show you how to do that, but you might want to give it a go. So what are the ramifications of undefined behavior? So for signed integers, x and y, x plus y invokes undefined behavior if the result is outside of the signed integer range. And a common wrong belief that I used to hold is that this undefined behavior is localized. Like, if you do z becomes equal to x plus y, and if x plus y are out of range, then z gets an indeterminate result. So it's like you've got the semantics. Z becomes equal to, if the sum is in signed range of x and y, then x plus y, otherwise star, meaning anything. So I used to think it worked like this, that if you added these things together, then if the result doesn't overflow, you get the result. And if it overflows, you get anything. Okay? But actually, the situation is much more drastic. The reality is, if the C program P invokes undefined behavior when executed on an input I, there are no guarantees about what P will do when you run it on I. It's not that it will go wrong in the places where you did the undefined behavior. More severe things can happen. And I'll try and make it clear why, because clearly, like, no one is trying to give you a hard time. It's not like compiler writers hate you and are trying to make the compiler do horrible things to your program. Compiler writers love you. They want your program to go really fast. And that's the problem. OK, so now I'm going to use some material which I've got from John Regere's blog posts about undefined behavior. So John Regere at the University of Utah has got this blog called Embedded in Academia, which is really good. About once a month or so, he publishes a post, and they're really readable, really, really fun and interesting posts. And he's got, I think, the best series of articles about undefined behavior that I have read, and the following slides are adapted from his blog. So there's a C, frequently asked questions, and it defines undefined behavior to be the following. Anything at all can happen. The standard imposes no requirements. The program may fail to compile, or it may execute incorrectly, either crashing or silently generating incorrect results. Or it may fortuitously do exactly what the programmer intended. Okay? And a common misconception, and this is quoting John, is the following. It's very common for people to say something like this. The x86 add instruction is used to implement C's add operation. By and large, that's true, right? If you're compiling for x86 and some addition occurs, probably will occur in your x86 processor. It has 2's complement behavior when the result overflows. I'm developing for an x86 platform, so I should be able to expect 2's complement semantics when 32-bit signed integers overflow. So this is wrong, and it's like saying, somebody once told me that in basketball, you can't hold the ball and run. I got a basketball and tried it, and it worked just fine. He obviously didn't understand basketball. Right? So just because in your experience this has worked out doesn't mean that it will work out. OK. So why is it a misconception? Well, the point is that the programming language has got a set of rules that are reasonably well defined in the case of undefined behaviors in C, even though they're quite long, but they're reasonably well defined. And the compiler assumes you've obeyed the rules when it optimizes your code. The compiler might give you warnings if it can detect that you haven't, but often the compiler doesn't know whether you've obeyed the rules or not. It will just assume you have, and it will do as best it can to make your code run as fast as possible under the assumption you've obeyed the rules. Okay? And if you break the rules, then compiler optimizations might cause your code to behave unexpectedly from your perspective, regardless of what the hardware does. So people often say things that I think are really stupid and unhelpful, like, if your program's got undefined behavior, the compiler could format your hard drive. Or if your program's got undefined behavior, the compiler could launch NetHack in the background. And I think that's really unhelpful because it completely misses the point. The compiler's not out to get you. The compiler just wants to compile your program. So I'm going to try and show you the compiler's thought process, let's say, when compiling a program, and show you that the compiler gives you these weird results by actually doing a sensible and good job of compiling your program. So the compiler has got the following job. Number one, it should generate code that respects the language specification. It's not going to try and generate code that does what you want it to do. It generates code that respects the language specification. Okay? Number two, and this has to be secondary, but it is important, is it generates efficient code. And this is important for most applications we run. If you're, say, compiling code to run on a plane, you tend to compile with no optimizations. But if you're compiling, say, a computer game or an operating system, you really do want compiler optimizations to be enabled. And a compiler can assume your program doesn't exhibit undefined behaviors. If your program does exhibit undefined behaviors, then any behavior is acceptable. So no matter what the compiler did, it's OK. So it's not that the compiler is looking for undefined behavior and trying to generate weird code. It's rather assuming there isn't any undefined behavior and trying to generate efficient code under that assumption. So let me make this concrete by showing you the compiler's thought process on this example. So here's the code we wrote. So let's be the compiler for a minute. I wish compilers actually thought like this, but obviously they don't. But this is roughly what the compiler's reasoning entails. So I will assume this program does not exhibit undefined behavior, because if it does, then it doesn't matter what code I emit. So I can assume that there are no UBs. I know x plus y doesn't overflow, because if it did, the program would exhibit undefined behavior. I also know that it's impossible for x to be positive, y to be positive, and x plus y to be negative unless the program overflowed. Right? So x plus y has to be positive. So the condition's equivalent to false. Excellent. My job is to optimize the program, so I will replace the condition with false. By similar reasoning, the second condition is equivalent to false. So the compiler can simplify the program to, if false, return int max, if false, return int min. And then the compiler can apply dead code elimination and do even better. It can give it this behavior, return x plus y. And really, we have to say to the compiler, well done, full marks, you've optimized the hell out of this program, because, you know, the program will run faster now because you've eliminated 2 branches. Right? But the ironic thing is that we've got the program that we were trying to avoid. We've got normal addition. And now what happens at runtime? Well, this program gets compiled. And for x86, the compiler does indeed generate an instruction that wraps around. And we actually do get wraparound behavior. And that's why when we run the program on those big inputs, we get exactly what we were trying to avoid. Right? So ironically, that's what we had anticipated would happen and we're trying to avoid. The compiler undid all of our good work. Yeah? So we could get around this problem in one of 2 ways. We could make the code really confusing so the compiler wouldn't be able to optimize it. All right, so we could make, say, I mean, I'll show you if you want. Like, we could do something like, oh, sorry. Thank you. Appreciate it. OK, we could do something like this. Volatile int t equals x. And then use t here. So volatile says to the compiler, you can't assume anything about this variable. You can't, it keeps its value. There we go. Okay, so we use volatile to stop the compiler from doing its job. And then we got the results we wanted, right? So if we make the program more complicated, then we could make the program go away. Or the right thing to do is to rewrite the program so it doesn't invoke undefined behavior. And then the compiler will be able to do optimizations that don't break our intention as programmers. Okay, but I sound like I'm on the compiler side here. But really the point is it's a tricky situation where programmers don't read the C language spec. They're not language lawyers. They don't learn all the rules. They program using examples. They learn from the web. They program from asking their friends. They program by remembering what C# does and trying it in Java, or the vice versa, right? Yeah. That depends on how much the compiler does copy propagation. The compiler might end up in the same situation. So yeah. But you know, the compiler optimizations are very fragile. They have preconditions about when they apply, and if essentially you can obfuscate the code enough to break those preconditions, then the code will do what you wanted it to do. But Lemmy says that's the wrong approach to take. I mean, it's just, yeah. Okay. A security critical example is as follows. So, look, I don't think I'm going to go through this one in so much detail. I just want to show you that basically there's a check that says, if this pointer is null, return pol error. Okay? And what the compiler says is, right, well, can that pointer be null? Well, you've looked up its SK field, right? So by looking up its SK field, you've told me it's not null. Because if it's null, the program has undefined behavior. And I'm just assuming it doesn't have undefined behavior. So I can optimize away that check. Okay? So the program's reasoning is, if tull is null, either that will abort, right? Or if address 0 happens to be mapped, which apparently it can be in some processes, then not ton will hold and pol error will be returned. But the compiler thinks, well, the program is telling me that this is not null, because otherwise ton arrow sk would give a null pointer exception, so I can optimize with this block of code. If ton is 0, but ton sk doesn't abort because address 0 is mapped, then execution continues after this point, and you get a bad socket structure. And apparently this was the basis for a privileged escalation attack, which you can read about here. Yeah. So it's really difficult. There's been various proposals for having a friendly dialect of C with different rules for undefined behavior, and I think there are numerous problems. One problem is that compiler developers are resistant to changing their stance on undefined behavior for a couple of reasons. First of all, they do well on these benchmarks that apparently compiler developers care about. And second, the compilers are pretty complicated and the optimizations are quite sophisticated, and trying to work out all the places where undefined behavior is being exploited would be non-trivial. So I think making them more local would be hard. Yeah. I think that there is a feeling in the community that compiler developers should really only try and exploit undefined behavior if it seems reasonable to do so. So the example I showed you, the saturating add, there must be some code in there that really does a bit of clever reasoning, saying, okay, that's positive, you're adding them, that can't be positive, so this is equivalent to false. Maybe that could just be removed. Maybe that's not a good optimization to be doing it. I wonder, has anyone studied how much these UB exploiting optimizations are actually speeding up programs around the world, rather than just causing sort of bugs in programs? So yeah, I don't really have an answer to your question, but I think it's definitely interesting and something that could merit further research. Like, another thing the compiler does is works out that the square of a number is positive and exploits that. I mean, someone's written code that figures that out and exploits it. Laurie? In terms of its performance impact. Right. Yeah, and I don't know enough about undefined behavior to know whether O3 fires up the. Yep. So yeah, I'm not sure at what level. I mean, even no optimizations, it still does some optimization in GCC, apparently. Yeah. Yeah. And how do you get people to agree on that? It's very difficult. So, yeah. Yeah. No, I think trying to change widely adopted standards is really difficult, and everyone's got different things they care about. You know, some people care a lot about performance, some people care about legacy hardware, so it's hard. Let me at least say a few words about why we have these undefined behaviors. Yeah. Oh, sure, I think you could, yes. I think, for example, you could say that a division by 0 may abort the program or may return any result, but you don't say it makes the program completely undefined. You might say reading from a null pointer may abort the program, may give any result, but it doesn't make the program completely undefined. And then the reasoning that the programmer had used in that example I just showed would maybe hold, right? That, you know, either this thing will abort or the check will not, you know, optimizing away these checks is the big problem. Yep.
This would still go towards your point that there are people with different motivations for what they expect, right?
Yeah.
Because seemingly there is no other LPC, LLVM specs anywhere that people actually understand these legacy optimizations, right? Like C and C++ spec, the Java spec, these are not specifications that are actually targeting real people, targeting compilers.
Yeah.
Right? And so it's like, you know, that is a totally reasonable thing for me to watch from the spec that says I put people to programming in, but these aren't specs designed for people programming.
Right. So I mean, maybe I think we should continue this discussion over dinner and drinks. Yeah. So very cool discussed stuff. So I want to finish today by giving you 2 reasons why languages have undefined behavior, because all I've really done is said, all I've really done is said that they do. I want to just give you, it's not completely crazy. So first of all, there is diverse hardware out there. So x86 signed edition wraps on overflow. On MIPS, signed edition traps on overflow. And I had to Google this, and I don't know if it's really true, but apparently there's some legacy system that uses 1's complement representation. It doesn't use 2's complement representation. So historically, at least, there were reasons to have this undefined in the standard to cater for multiple implementations. Shifting. So if you left shift the value 1 by 32 bits in a 32-bit register, what actually happens at the hardware level? Well, on ARM and PowerPC, you get the result 0. On x86, you get the result 1. So you get these different results. Okay, so remember that. So if you dereference null, on x86, dereferencing null gives you a runtime exception unless you map 0 to a valid page, and on ARM, address 0 holds exception handlers, so the semantics are different. Okay. If you standardize behavior in the standard, then you force some platforms to take a performance hit, and that might be a problem for them. For example, if you specify wraparound behavior for signed addition, that would be free on x86, because that's what it does. But on MIPS, you would have to have some checking code, because otherwise you would get an exception. If you define overshifting to always yield 0, so if you shift 1 by 32 bits in a 32-bit register, and you want to give the result 0, then you've got to compile x left shift y to, if y is larger than 31, then 0, otherwise x left shift y. And that might be expensive, and that might not be something that people want. So I'm not saying that these are good reasons, I'm just saying that they are reasons. Okay. And another reason is that some optimizations you really might want don't apply unless you assume undefined behavior freedom. So for example, if you have a look at this little program, find, so it's got an array of integers a value x to be sought, and an integer n, and what it's going to do is loop while I is less than or equal to n. And if ai is equal to x, return true. And if it doesn't find x, return false. So on a 64-bit architecture, pointers are 64-bit values, but integers are 32-bit values. So if you compile this code for a 64-bit architecture, then ai, the indexing of the array a with the value I, that requires I to be extended to 64 bits so that you can index into the array, because I is an integer, okay, an int, and a is a pointer, int pointer, right? So, yep. I don't actually know the technical reasons, I confess. So, but my understanding is that you can't directly think you need either a different instruction or you need to operate on certain registers, and you need to actually say, right, put this into an appropriate register, or extend it appropriately so that you can do the indexing. Yeah. So yeah, an optimization then would be, well, why don't we change I to have type long, which is 64-bit, right? So then we don't need to do this promotion. But the trouble is that that optimization only works if I++ doesn't overflow. Because if I++ overflows, then, and if we assume we've got wraparound behavior, then with 32-bit integers, this program has got an infinite loop if n is int max, right? Because if n is int max, then I can reach int max, and then we increment it, and it becomes 0 again, and we keep executing. But if we change I to have type long, then I can be less than or equal to int max. We can increment it, and it becomes int max plus 1, and then we exit the loop. So this is an example where an optimization we would like to be able to do is only possible because we assume there's no undefined behavior. So, excuse me, yes, you're right. So yeah, because we're assigned here, so if n was int max, if I reached int max and we increment it with 32-bit wraparound, it would become int min. Absolutely, you're right. Yep. Whereas if I was a long, we would simply go to int max plus 1. So this would change the semantics of the program. If instead we say, under that crazy scenario, the program doesn't have semantics, we can do the optimization. So there are arguments for having this kind of behavior. OK, so I'm going to stop there for today. And tomorrow, what I will talk to you about is random program generation, give you a tour of the C-Smith tool from the University of Utah, and then I'll talk about metamorphic compiler testing and tell you a bit about the GLFuzz tool we've been developing at Imperial College London. Thanks very much.